Okay. Thank you everyone. My name is Harrington. I'm a building physics specialist. I work at Daines School. And I'm here to present a talk building simulation for a Rolls Royce Factory ventilation retrofit. The factory in question is divided into 4 different areas. The factory is divided into 4 areas. The sort of top, which is involved in smelting metal, which is cold, which is shaken metal, and maintenance of die, which has a loading door where they get things delivered and where they maintain equipment. And there's also RSS, which basically puts airplane engines together. And our brief was to look at the ventilation system. The factory evolved over time. More heat generating processes were incorporated into the factory, and they had addressed heat issues by including more and more local extracts. And the local extracts had resulted in under pressurisation of RSS, and that led to 2 problems. One, a negative pressure on RS brought in air from forges, and that brought in a lot of carbon dust, which caused cleaning problems. And also, in winter time, the makeup air for local extracts was movers, and the airflow, temporary airflows and movers were creating minimal discomfort for the workers. Now, by modelling, we could use the desktop study to sort out the negative pressures in the factory. Or modelling allows us to look at things like energy distribution, particularly using CFD. CFD is able to model stratification well. It's able to identify hotspots and cold spots. Once you understand where the hotspots and cold spots are, you're able to test mitigation methods. But the downside of CFD is very computationally intensive, so we've used thermal modelling to look at temperatures across the whole year to identify peak summer and peak winter conditions, and then to work out surface temperatures that could be used for the inputs in the CFD model. A lot of boundary conditions in such a big factory, there's thousands in fact, so earlier we decided to automate the process. So we wrote a Python script to read in all the boundary conditions from an Excel file, and then this would output a macro file that could be run in the CFD software, and it meant that the boundary condition setup was the one-click operation rather than taking thousands of mouse. The data in the model comes from a number of areas, mostly from site survey, so we were able to trace electrical loads from bus bars and substations to individual and sets of equipment, and therefore assign a heat count to them. In forges where we have less nuanced data, we were able to use thermal imaging to work out which hot bits of kit. We used handheld thermometers to take rate readings in the doorways between the different areas of the factory. So the results we were able to give Rolls Royce included things like service temperature, occupied level. They were able to see that the hotspots and cold spots predicted by the model tallied up with the extremes on site. We were able to give them velocity plots showing before and after our designs were implemented. Before, there's a high inflow through the loading doors in maintenance and die, and a flow from forges into our RSS, bringing all that carbon particulates. And when we finish the design and implement it, there's a flow in the opposite direction, less flow through the loading doors, and obviously better comfort from that perspective. So how do we achieve this? We achieve this with high-level extracts in RRS. These extracts are up, down, or up, depending on what local extracts we're doing in that at the time. We adapted the low-level supplies, providing baffles and dampers also that could be worked on maturity. And we added fabric ducts into forges to get cold outside air into the environment region. So that concludes my talk today. Thanks very much for listening.
Okay, we'll take a question from
Hi there, What was the major challenge? I guess the question is, if you were going to go back and start again, what would improvements would you make to the system with the knowledge you now have?
The hardest part was definitely the data collection. The hardest part was definitely the data collection to get the model inputs, because there's so many different heat generating kits, so many extras, so many suppliers, so that the majority of the time was actually not modelling, it was extensive there. I think it's we need the CFD to be accurate enough to be able to test mitigation. We don't need it to be super accurate to get the exact temperatures in the right places. So we feel that model actually did this. We were able to test mitigation.
Great. Thank you, Liam. Thank you, Liam. 4 minutes and 45 seconds. Fantastic. Should get extra marks for that. Okay, the next.